In this lesson, we will consider another elementary theorem, this time involving current sources. Okay? I will call that splitting a current source. It will be clear why it is called that way. Now, let us say we have some circuit, could be any circuit. Okay. And it has a current source. I have not imposed any restrictions on this circuit. Okay. It could be linear, non-linear, whatever, and it has this ideal current source connected somewhere. Okay. Let us say the value is I naught. Now, it is clear that this is exactly equivalent to two identical current sources in series. In fact, we cannot in general connect current sources in series except when they have identical values. And if they have identical values, then the series combination is equivalent to a single current source. That is, if we have two currents of I naught in series, it is exactly equivalent to having a single source also of I naught in series. Okay. Now, what is the point of this? If you consider this middle node, okay, then the current coming from here is I naught and the current going there is I naught. And even if you have a wire that is going elsewhere, let us say it is connected, the current in that will be exactly equal to 0 because of Kirchhoff's current law, okay, because this is I naught, that is I naught, that has to be 0. So, now combine this with the fact that an ideal current source will provide the same current regardless of what voltage is across it. We can connect this to any other node in the circuit. Let us say we have some node here, we can connect it, because this current is 0, right. Imagine that this is a node with a number of connections, and before making this connection, the sum of all those currents will be 0, and this is just adding 0 current. So, this is really not contributing anything at all to the Kirchhoff's current law equation at that node. So, you can make this connection without disturbing the rest of the circuit. Okay. So, to summarize, if I have an ideal current source in a circuit, I can think of it as two ideal current sources of identical values in series, and the midpoint can be connected to any node in the circuit because that carries 0 current. These two currents are exactly equal to each other. So, it has to carry 0 current. So, it will not disturb any of the other nodes in the circuit, okay. And these current sources can work with any voltage across them. That is the meaning of an ideal current source. So, if you connect this to some other node and change the voltage across the current source, nothing happens, okay. So, this is known as splitting the current source. You can when you have an ideal current source, you can imagine that as being two identical current sources in series and connect the midpoint to any point in the circuit, okay. Now, what is the use of this? So, let us say we have a circuit and there is some node we think of as the reference node, okay. Now, I have a current source like this, and I will split it into two sources in series, okay. Now, I can connect this to any node, and let us say I choose to connect it to the reference node. So, then I will redraw this circuit as this one. So, let us say this was point 1 and point 2. So, from point 1, we have a current source going to the reference node of value I naught. All these are of value I naught, by the way. And from point 2, we have another current source also going to the reference node. Now, what is the difference between this and that? In this, we have a current source between some two nodes of the circuit, neither of which is a reference node. In this, we have two current sources, but these current sources have one of their terminals connected to the reference node. Now, it turns out that in many cases, it is easier to analyze circuits when the source is connected to the reference node. Okay. Now, we won't be able to appreciate it without any examples, but just take it from me that many times it is easier to analyze circuits like this. So, that is why this business of splitting the current source is helpful. Okay. Just to illustrate this point, let me take the example I had taken long back while discussing nodal analysis. I had I1, I3 and R11, R12, R22, R23, R33. Now, I had discussed circuits like this, if not exactly this one. Let us say I have this current source. I call this a floating current source if neither of its terminal is connected to the reference node. The reference node is over here. Okay. Now, please pause at this point and write down the nodal equations. I am going to write it as well and you can compare the results just for extra practice. So, if I do that, I will have, let me number the nodes like this 1, 2 and 3. I will have G11 plus G12 minus G12, 0 minus G12, G12 plus G22 plus G23 minus G23, 0 minus G23 and G33 plus G23 times V1, V2, V3 equals total current pushing into node 1, which is I1 plus I0, total current pushing into node 2, which is 0, total current pushing into node 3, which is I3 minus I0. Okay. Now, let me do the current source splitting business on this circuit. Now, let me carry out the splitting of current source business on this circuit. I will erase this and connect two identical current sources in series, I0 and I0. Okay. And this middle node I connect to the reference node. I said this is the useful part, right. Now, you see that this current source is between this node and the reference node, therefore, it is in parallel with this one. Okay. So, what we will have is I1 plus I0. This is between node 3 and the reference node and it is in opposite direction to I3. So, on this side we will have I3 minus I0. Okay. And the rest of the circuit is as before. Okay. Now, the conductances in the circuit have not changed at all. They have exactly the same arrangement as before. This is node 1, 2, 3 and the reference node. So, the conductance matrix, basically the left hand side of the equation remains the same. I will copy it over from the previous case. The only things that have changed are the current sources. Now, here I have two current sources instead of 3, but in the first row of this right hand side vector, I have to have the total current source pushing into node 1, which is I1 plus I0, and for node 2 it is 0, and for node 3 it is the total current pushing into node 3, which is I 3 minus I 0. If you go back here, you see that it is exactly the same set of equations we have got. So, clearly the solution to this circuit with the split current sources and the split point connected to another node will be exactly the same as for the original circuit, okay, because the equations are the same. So, that illustrates my point that when you have a current source connected between any two nodes, you can think of it as a series combination of two current sources and connect the midpoint of those to any other node in the circuit without altering the solution. Okay. Now, in this case I tied it to the reference node. Usually that is what we will do to make our circuit analysis easy, but it could be tied to any other node. In fact, you can try it with this circuit also. You can tie it to any other node and the equations will remain exactly the same, which means that the solutions will remain the same and nothing has changed in the circuit. Okay.